Everyone. So this is going to be test one review for the final, going over one of the versions from this semester. So to start off, just doing some foundational naming practice. So with naming, making sure to always highlight that longest chain, and then make sure you always are numbering your carbons. And in this case, you can number two different ways. And that blue numbering right there is going to give us that 3, 4 numbering rather than the 4, 5. So we're going to go with the blue. So it's going to be 3, 4 dimethyl. Our parent chain is 7, so it's going to be heptane. Moving on to our next one. So we have our functional group alcohol. Alcohols take the biggest priority out of any of the functional groups. Then we're just going to number 1, 2, 3, 4, 5, 6. We go the other way. The alcohol gets 4, so this is our preferred numbering pattern. So it's going to be 5 bromo, and the bromo comes before the chloro just because of alphabetical order. The numbers do not matter. It's based on the alphabetical order when listing them in the name. And then our parent chain is hexane. But with our alcohol, it's going to be hexane. Drop the E, dash, 3, dash all. Now this one right here has an amine as our functional group. And on our fourth carbon right there, we have a methoxy group. So it's going to be 4 methoxy. Our parent chain is pentane. We pentan 2 amine because that's how we write out those amino groups when it's a functional group. Moving on to our next one. So this one's a little bit trickier. We have a ring. So a lot of times people struggle with naming or numbering rings. So in this case, we need to start right here with this 1 because that's going to give us 1, 1. And if we start anywhere else, it's going to give us a 1, 2, 2. So this is the best place to start. So we can go, and then we need to look at our chlorine versus our methyl. The chlorine is higher alphabetically, so we're going to go 2, 3, 4, 5, 6. So when we start naming, it's going to be 1 bromo, 2 chloro, 1 6 dimethyl cyclohexane. Moving on to our next one, we have another ring. So here we also have another functional group. We have our amino group right here, or our amine group. So that's going to be our 1. We need to look what's the next point of difference. So here we have methyl. Here we have methoxy. So that O comes before that Y. So we're going to go 2, 3, 4, 5, 6. So we're going to have 3 methoxy, 4, 5 dimethyl. And remembering that prefixes don't affect the order. It's based on the parent name of the branch where the name goes in the list. So 3-methoxy, 4,5 dimethyl. Then we have a cyclohexane ring again. But this time we have an amino group there. So it's going to be cyclohexane, no E right there. And you can either do 1 amine or cyclohexanamine with no 1. The 1 is redundant in this case since it's that functional group. Moving on to the next one. So here we have alcohols and amines. So our two functional groups, but in this case, alcohol is the priority functional group because it's the highest on our list. So that means we want to make sure our alcohol has the lowest possible numbering. So if we look here, we have 1, 2, 3, 4, 5. And we have 1, 2, 3, 4, 5. So our red scheme gives us a 2, 3, 5, and then green gives us 1, 3, 4. So we're going to go with that 1, 3, 4. So it's going to be 1, 4 diamino, and our parent chain is pentane. So it's going to be pentan. Got that E, 3 all. Now we can move on to the yes and no naming. So with these, the trick is honestly to name it yourself. So if we look at our longest parent chain here, which is that, we can go 1, 2, 3, 4, 5, 6, 7, 8. Our longest parent chain is octane, so that automatically means that this name is not right. This is no. Moving on to our next one. So rings can be a little bit tricky, because it's kind of sometimes hard to choose where to start. But with our group here, so we're going to start with our alcohol being one, so that's good. And then alphabetically, we either can go to chloro or amino, and that amino group is going to take priority. So it's going to be 1, 2, 3, 4, 5. So 3 amino, 4 chloro, cyclopentane, 1 all. That is right, so it's going to be yes. Moving on to the last one, we once again follow the same kind of steps. We can start numbering here with our chloro because it's alphabetically better than the methoxy. And in this case, our actual name would be 1 chloro 4 methoxy butane. So this one is no, it is not correct. Moving on to some hybridization. So this stuff is things we have not seen since test one. We kind of brushed over it, but it's important to practice, make sure that you understand it and know it for the test. So looking at hybridization, so C4 right here has 3 bonds. So it has this one right here, that bond, and then this double bond. So that makes 3 groups. You might think that the double bond makes it 4 groups, but it's the overall, like how many atoms technically are bonded or how many a lone pair counts as a atom in that way. But in this case, it has those 4 bonds, the 3 groups, so it's going to be 100 is going to be sp2. Then we look at O1. O1 right here has these lone pairs, so this means we're going to have 4 groups since we're bonded to 2 atoms and we have those 2 lone pairs, so it's going to be sp3. Moving on to the C6, C7, O5 bond angle. So the atom we're actually looking at is the C7 atom when we're looking at the bond angle. So that atom is bonded to 4 different atoms. So that's going to be our tetrahedral, which is 109.5 degrees. Now looking at our O1, C1, C2, so that's right here. That's bonded to 3 groups, no lone pairs. So we know that that is trigonoplanar and is 120 degrees. Our last bond angle is C3N1, C4, which is right here. That nitrogen has a lone pair on it. So this is going to be that trigonal pyramidal with that lone pair on there as one of those groups. So it's going to be less than 109.5. Next, we are looking at our classifications of carbon. So we practiced a lot with this all semester, but so you should be pretty good at this by now. But if we look at C6, C6 is, and highlight in green, is bonded to this carbon, this carbon, this carbon, and that carbon. So C6 has 4 carbon connections, making it a 4' carbon. Lastly, the most acidic proton. So basically, we're looking for something with a that methyl with a oxygen and a hydrogen. That's usually a good sign um, for proton or for acid, the most acidic acid or proton. And over here at this end, this C double bonded oxygen helps pull some of that charge away from that oxygen, making this proton on the O1 oxygen the most acidic. So our answer is O1. Now moving down to isomers and things like that. So with isomers, at least for test one, the only time you have stereoisomers is when you have rings or chairs and you are able to tell the direction of the groups. Otherwise, it's going to be the constitutional isomers different or the same. But for the final, it'll be more like test two with the enantiomers, diastereomers, and things like that. So looking at this first one, they kind of look different a little bit, but if we count the overall molecular formula, they end up having the same molecular formula. So now we need to see if they're constitutional isomers or if they're the exact same. And to do that, you can check the names. So our longest parent chain is this heptane right here. And we have a 3,4, so it's going to be 3,4 dimethyl heptane. And over here we have 1, 2, 3, 4, 5, 6, 7, 3, 4, dimethyl heptane. So these are the same because they do look a little different drawn out the way that they are, but they are the same based on their names. Um, and that's something to check for when you're trying to decide between same and constitutional isomers. But always start with looking at that molecular formula first. Make sure you're not missing anything and that you don't accidentally miss an easy one because you're able to put different. So moving on to the next one, we have this right here. So when I have a chair and kind of that planar cyclohexane like that, I like to draw my groups out like this. So this is our 1, 2, 3. So 1, 2, 3. So that chlorine is up, H would be down, CH3 is up, H is down, Br is up, H is down. So we have a difference at our CH3 and H group right here. So these are going to be stereoisomers because this one is fully cis, right? Let's see. This one is cis, and then this one has that one trans ethyl compared to the rest. So these are going to be stereoisomers. Moving on to this next one, I like to do the same thing. So we have another ring, we have another chair, draw you out a ring, easier to show it. We have CH3 going up, so we can make that our wedge, or chlorine going up, sorry. And we have another chlorine going up on the 2 carbon. So if we number 1, 2, 1, 2. So they're on the same carbons, so they're not constitutional isomers. They're not different. So that means you need to decide if they're the same or stereoisomers. In this case, we have a trans molecule over here with the up and the down, and here we have cis. So once again, this is stereoisomers. So I'm moving down here. With Newman projections, I like to kind of draw them out. So your two center carbons like this. This is the front carbon, or sorry, the back carbon with the ring, and then our front carbon is on the spokes, I like to call it. So our back carbon has a CH3 group attached, another CH3, and an H. Our front carbon has an H, and then a CH3. Then over here we can do the same thing. We do our first, our front and back, or back and front. So back we have just 3 hydrogens, so CH3, and our front has these carbons like this. So now we have to look at the name. So when we do that, right here we get 2-methyl butane, and then over here we get 2,2-dimethyl propane. And that means since the names are different, the connectivity is going to be different, and that gives us constitutional isomers. Then moving over to this one. So here we can kind of look at our groups and decide what we have going on. So when we do this, we can number 1, 2, 3, 4, 1, 2, 3, 4. So this one has all groups up. This has all groups down. But in reality, if you flipped this one, all groups would be up, which makes them the same to one another. Moving on to the general knowledge page. This page is usually where people struggle the most on the test. It's some of the more niche things in the class, some things that require a little bit more memorization to do. But 4 degrees of unsaturation, so it's number of C's minus 1/2 H, and then I think minus one half halogens plus one half nitrogens. But for this semester, I think you only need to worry about the carbons and the hydrogens. So it's going to be 7 minus 12 over 2. Then it's at the end of the formula is plus 1, and then plus 1. So 7 minus 6 plus 1 equals 2. Now looking at the most acidic proton. So once again, this is kind of going back to that inductive effect. So we're looking for the proton that has the most or the most acidity or the most likely to let go from their oxygen. So with this boron right here, it has the inductive effect and it's kind of pulling charge away, allowing that proton to leave. So this is the most acidic proton. For carbon disulfide, so this the best way to tell if it's polar or non-polar is to draw out the structure. So if we draw this out, so we have C equals 4 electrons, S2 is going to equal 12, each one's 6. That means we have a total of 16. So if we do our bond like this, so that's 1, 2, 3, 4. Right now we used 8 in our lone pairs. Make sure that those sulfurs are their octets are full and they're happy and with no charge and everything. So this is going to be a non-polar molecule because it's linear in this fashion and there's no lone pair pushing things down or any group that has a different electronegativity. Moving on to the carbon-carbon single bond length. So this is something we need to know, single, double, and triple. So a single, so the answer for this question is 1.54. Um, just knowing the double and the triple as well. I believe they're 1.3 and 1.2 respectively will be helpful, just in case you ask it. So here we have a planar cyclohexane. So these different rings with the different strains and stuff like that are something you just kind of need to memorize. Um, Harper has something really, really good in her TA folder for this. So I would look at that and look for the bond or look for the strain document, and it'll tell you everything you need to know for strain. But in this case, planar cyclohexane has both bond angle strain and torsional strain. Moving on to this next one. So this is a chair conformation, and we have that methyl group, equatorial, and that H axial. So Gauss strain is basically when you have like two large groups together. And in this case, the hydrogen is not considered big enough to cause that type of strain. So there's none of that. Flagpole, flagpole is usually only really found um, in our boat structures, if I could draw it. Something kind of like that. Not exactly, but this is where you find flagpole because you have the groups kind of going up like that. But you will never see flagpole really in a chair conformation. And we have to look at 1,3 diaxial. So 1,3 diaxial would be true if that methyl group right here was axial, but it's equatorial. So there's no steric strain here. I'm moving on to the acid and pKa questions. So with this, whatever direction the reaction is going to go, it's going to go towards the weaker acid. So if we look at the pKa, so HF has a pKa of 3, and then NH4 has one around 10. So, and you'll get the pKa table on the test, at least somewhat filled out. So you don't have to worry about like memorizing everything. I would definitely know like the big ones like alcohol, some of the like alkyne pKas and stuff like that. So now pKa, so low pKa equals strong acid. So since that pKa of 10 is higher, that's our weak acid. So this reaction is going to go to the left. I'm moving on to the next one. So this is another example of the inductive effect in action. So right off the bat, this is not going to be it. This is not going to be it. And then we need to look at our other ones. So the most electronegative atom that we have to work with is fluorine. So that kind of automatically rules out the chlorine one. We know the fluorine is going to be stronger. So with the two left on the that we have to look and see what causes the strongest overall effect. And so with this double bond of oxygen being there, it adds to the effect. And it's going to be our answer over this one because the fluorine alone is not quite as strong. So this next one's a little bit tricky. So we're looking for water soluble molecule. So right off the bat, this chlorine can't do anything. That cannot do anything, and neither can that one. And that's all because they don't hydrogen bond. And that's kind of like the rule for water soluble, is that they can cause hydrogen bonds. So hydrogen bonds happen with those fun atoms. So they fluorine, oxygen, and nitrogen. So we have NH2 and then we have an OH. So both of them can hydrogen bond. However, 5 carbons or greater is not soluble. We have one, two, three, four, five. So unfortunately, that one's not going to be the answer. And only this one is because of the carbon chain link. A lot of people get confused. They see that OH and think hydrogen bond instantly, which is usually true. But when you hit that kind of carbon chain limit, it's not as soluble. So now moving on to bicyclic naming, something that we did a little bit for test one. So the trick is for this one, you start on the biggest side of the ring and then to try to get your groups at the lowest overall numbers. So we're going to start right here. 1, 2, 3, 4, 5, 6, 7. And then your last number will jump into the middle like that for 8. So we have 3 carbons on this side, 2 there, and then we have 1 in the center like that. That'll be important for when we actually start naming it. So to start off, it's 6-methyl. And then this is where it's different than other names. So it's bicyclo. We have our brackets like this, and then we do the numbers in descending order. So it's going to be 3, 2, 1. And that's from each side of the ring, and then the bridgehead in the middle. And then we just throw on the parent, which is octane. And that's all we do for that. Moving on to branch naming. So highlight the longest possible branch off of the main chain like this. In this case, we have a nice straight hexane chain. So then we number it. And so it's going to be hexane, no E. And then we have to look at where it's attached. So where does it attach to the main chain? It's that 2 carbons. So it's going to be hexane 2 and then ill. Moving on to the last bit of stuff for this. So this is something, the energy conformation is basically looking at the Gauss strain um, and seeing which ones have the most, which ones have the least, and like just understanding energy stuff and being able to like transfer from one diagram to another and flip it with a green flip and stuff like that. So when we're looking at this one, we can go ahead and just add our CH2, CH3, H, and H. And that's from our original, looking at the back carbon, and then our front, we just rotate it slightly to make it look the way that it wants to. Our CH3 down here, and then H up there. So then all that we do for this is rotate the front. So we're going to move basically that one, do it in a color. This methyl's going there, that methyl's going there, and that hydrogen's going there. So we can show that by H, CH3, CH3, and then leaving our back carbon the same, CH2, CH3, H, H. Then we're going to do the same thing, so rotate again. CH3 here, CH3 there, hydrogen there, and then our back carbon once again, just staying the same. So now we can look at our types of strain. So here we have some strain. That's the only part. Same with this one. We have the same level of strain as the one on the left. But then this one, we have double the strain compared to the other ones. So our two highest energy, or the lowest energy conformations are these two over here. Making sure to circle both, not just one. So for this one, we have to read the name. So let me erase this line a little bit. It's a cis 1 ethyl 4 methyl. So automatically we know that our ethyl is going to go right here, and that's a CH2 CH3 group. Don't forget to add that hydrogen right there. And then our 4 methyl is also cis, so it's going to be up there. Don't forget that hydrogen there. So then when we transfer, it's going to be CH2 CH3 up, H down, and then again CH3 up, H down. Then we do our ring flip. We go from axial to equatorial and equatorial to axial. So now, but they stay up. So this ethyl over here is now equatorial up. Hydrogen is axial down. And then CH3 up here is axial up. Hydrogen is equatorial down. So when we look at the lowest energy groups here, or the more stable conformation, we're looking for the biggest groups to be equatorial. And with that, this one right here has that ethyl group, which is larger than the methyl on the equatorial position. So that's going to be the more stable structure. Now, so basically just doing the same thing once again with this one. Transferring it is the really important part. So we have our one, if we number from here, 1, 2, 3, 4. So our one right here can go up, H down, CH3 down here because it's trans, and our last one being up. As long as you have that middle, the two carbon one being different than the one and the four, that's all that matters. You could have one and four be down and two up. It really just depends on how you draw it. But if you do it that way, you need to make sure that you carry it over the same way. So now putting our carbons here and our hydrogens, just like that. We have two groups axial, one group two methyls axial and one equatorial. And over here we have our ring flip. So all the groups are still in the same up or down position, but now we're looking at a different equatorial or axial position. On this one we have two in equatorial position right here on the right. So this one's going to be our more stable chair conformation. So that's pretty much it for test one, and this is the periodic table that you'll get. So good luck as you study for the exam. And if you have any questions, feel free to reach out and good luck on the final.